this video, we will cover molecular orbital energy level diagram. So this diagram is used to describe the bonding in a molecule using molecular orbital terms. Electron occupy molecular orbital according to the same rule developed for atomic orbital, such as Aufbau principle, Pauli exclusion principle, and Hund's rule. Please refer to this rule in your learning unit 1. To obtain MO description of the bonding in a molecule or ion, we need to follow this step. Okay, first step is draw the appropriate MO energy level diagram. Second, determine the total number of electrons, including inner shell electron and valence electron. And then the third step is we need to add this electron to the energy level diagram, putting each electron into the lowest energy level first. Okay, these are the rules pertaining to the arrangement of the electron into the energy level. Okay, the first one is a maximum of 2 electrons can occupy any given molecular orbital, and then only if they have opposite spin. Okay, this is Pauli exclusion principle. Okay, the second rules is electron must occupy all the orbitals of the same energy singly before pairing begins, and these must have parallel spin. So this is described by Hund's rule. Okay, for drawing the molecular orbital, there are few things that we need to consider. Okay, the first one is how to draw a molecule with total number of electrons lower than or equals to 14. Okay, example of the molecules are hydrogen, helium, lithium, beryllium, boron, carbon, and nitrogen. Okay, in this molecular orbital diagram, we first need to draw the atomic orbital first. Okay, this is the first step. We draw this one hydrogen. Okay, and then another one. Okay, and then 2s, and then another 2p. Okay, in this case, we are drawing nitrogen, for example. So this type of diagram, okay, can be drawn for H2 until N2. Okay, this is the arrangement for molecule with total number of electrons. Okay, first you draw the 1s, and then 2s, and then the 2p orbital. And you notice that, please take note of this part. Okay, and then when we draw molecule with total number of electrons more than 14, it is for molecules like oxygen, fluorine, and neon. Okay, we can draw it using this example. Okay, first 1s as usual, and then 2s, and then 2p. Notice that the 2p arrangement is different from molecule with a total number of electrons lower than 14. Okay, why the energy level is different between a molecule with less than 14 and molecules more than 14. This is less or same with 14. This one is more or same with 14. Okay, it is happen because the sigma 2s and sigma 2p interaction will cause the energy splitting. Okay, sigma 2p will go to higher energy while sigma 2s will go to lower energy. And in molecules having electron more than 14, it has small 2s 2p interaction. That's why, because it does not have much interaction, so the energy splitting is not much compared to the one with the large 2s 2p interaction. Like this, if these 2s interact with this 2p, they are going to repulse each other, and then they will go separate way, having a large gap in terms of the energy difference. Okay, from the molecular diagram, molecular orbital diagram, we can calculate the bond order and determine the bond stability of a molecule. Okay, the stability of a molecule depends on the bond order. So how do we calculate bond order is based on this equation. Okay, bond order is equals to number of bonding electron minus number of anti-bonding electron divided by 2. And then bond order corresponds to the number of bonds described by VBT. For example, if you have, using VBT theory, you have, for example, like H2O having single bond. So in molecular orbital, it will also show bond order of 1. For example, if bond order equals to 1, it is single bond. If bond order equals to 2, it means double bond. So if bond order is 3, it means triple bond. Okay, and fractional bond also exists in species that contain odd number of electrons. For example, NO and O2 minus. So if bond order is equals to 0, meaning that the molecule is not exist. And if bond order is more than 0, the molecule is more stable than the separate atom. For example, if let's say we have this N2 gas, so the bond order here is 3, which is triple bond. Meaning that this molecule of nitrogen gas is more stable compared to nitrogen atom. Okay, in drawing the molecular orbital diagram, there are two types of molecule. Okay, the first one is homonuclear, and the second one is heteronuclear. Homonuclear is when you have a molecule containing the same atom, for example H2, F2, and all that. Okay, while heteronuclear is a molecule that contains different atoms, for example HF, or OH, and etc. Okay, the first example here is the hydrogen molecule. So each hydrogen has only one valence electron, and they have same energy. And the configuration electron of atom is 1s1. Okay, in order to draw the molecular orbital, first step is we need to draw this one. Okay, 1s. So this is the first step. After that, we draw, this is the atomic orbital. Okay, atomic orbital. So in the middle here, H2 is the molecular orbital. Okay, what happened is that this one will split into two regions. Okay, this one is the bonding. This one is the anti-bonding. Okay, in this case, both hydrogen has one electron, then one electron. One will be contributed to here and one will be contributed to here, giving you two electrons. up and down. So since there are only 2 electrons, so you cannot put another electron in the anti-bonding region. Okay, to calculate the bond order, we need to calculate the number of electrons in bonding, which is 2, minus 0, which is 0 in here, divided by 2 equals to 1. Okay. For the next homonuclear molecule, which is the helium molecule, okay, for helium molecule, it is similar to hydrogen, except it has 2 more electrons. So this means 2 of the extra electron will occupy the anti-bonding region, yeah. Okay, so in this case, if we have, this is the first step. Okay, we draw 1s, and then when it is combined, it will give 1 electron, 2 electrons, 3 electrons, 4 electrons. Okay, this is 1, 2, and then 3, 4. So in this case, 2 electrons will go to the bonding orbital, and 2 electrons will go up to the anti-bonding orbital. Okay, when we calculate the bond order, it is 2 minus 2 divided by 2. Therefore, helium-2 gas does not exist. The one that exists only He gas. Okay, and then another example is O2 molecule. You know that oxygen has 2s and 2p. So oxygen has 6 valence electron because oxygen is from group 6. Okay, for 2s, we need to draw the electron in 2s. So both 2s has, okay, 1 electron here. So this is the atomic orbital of oxygen, and in the middle here is the MO of O2. Okay, 2 electron, 1, 2, 3, 4. Okay, you put in the middle, 1, 2, 3, 4. And then after that, at 2p, oxygen has another 4 electron. Okay, so this 4 electron, so how do we drawing it? Is first 1, 2, 3, 4, 5, 6, 7, 8. Okay, in this case, the bond order is 2, meaning it is a double bond compound. Okay, if bond order more than 0, it means that there are more electrons in the bonding molecular orbital than the anti-bonding molecular orbital, and such molecule would be more stable than the separate atom. In this case, oxygen 2 is more stable compared to oxygen atom. Okay, so that's all that is discussed in this video. So we will look at heteronuclear diatomic molecule in the next video.